Okay, thank you so much. I mean, it's great to be here. I see that actually two co-authors are here. So this is joint work with Fabian, Duncan, and Tobias. Fabian actually is visibly with this video. Duncan is hiding away, but Fabian for sure, and possibly Duncan will be also willing to answer questions in the chat. So I mean, if you really feel like, I mean, it's smallerish questions, I mean, don't hesitate. Just type them in. If it's smaller things, I mean, Duncan and Fabian can take care of. If it's anything more important, I wait for Sophie or Lionel to interrupt me, and then we can discuss along the way. So I can handle this very flexible. It's true that the title is now Quality of Life in a Dynamic Spatial Model. I appreciate that on the program, it's a slightly different title. We just changed it a little bit to have it a bit more compact and more impactful, but it's basically still the same story. It's about rows and rowback, but in a model with frictional migration. Okay, so let's get to talk here really. I need to make sure that my pointer is actually working. So I think I probably have to click here. So quality of life. I think the good starting point for this presentation is to quickly remind ourselves what quality of life is. I understand that you are a reasonably specialized group, so probably most of you have an idea, but let me just kind of run through it for those who are less into that literature. So the way I think about quality of life in economics is that quality of life is essentially an index that summarizes all location-specific amenities. Okay? You can think of things like clean air, good schools, low crime rates, all of these things increase your quality of life. It's obviously very difficult to measure all things that are relevant for quality of life and then assign the right weights. So what economists do, they make some assumptions, and then they look into wages in rents and indirectly infer this index, quality of life, from the spatial variation in wages and rents. And it's not that we actually, as economists, care so much about quality of life. I mean, of course, we do care about quality of life to some extent. But what we in particular like to do is we like to use quality of life to value non-marketed goods. Okay, so go back to the example we just had it, clean air. I mean, you want to put a value on clean air. How do you do it? There is no market price. So what people do is they recover quality of life from wages and rents. Then they correlate this index with some measure of good air. They get a value. Based on this value, they can conduct some kind of social cost benefit analysis and then decide whether a policy that would improve air quality is actually worth it. And the same goes for public schools, right? I mean, lower crime rates, transport infrastructures, all of these things. So it's actually a super important concept for a variety of fields in economics. What we've been doing for about 200 years, following from Ricardo really, is to assume a competitive equilibrium. So we really start from the idea that people are perfectly mobile. Under this assumption, the only equilibrium that can be stable is an equilibrium in which we have a constant reservation utility across all spatial units within homogeneous groups at least, okay? Once we have implemented that there is something like a constant reservation utility level, it's a very small step to simply say, okay, I mean, there is a compensating differential, so any variation that I see in real wages is just inversely related to quality of life. Okay, and that's what we do ever since Ricardo in the seminal Rosen-Rohrbeck framework, and we still do it in quantitative spatial models. Okay, now what's our contribution? Our contribution is to take this literature and bring a new class of spatial models to this literature, a pretty recent type of model, which is called the dynamic spatial model. Okay, the dynamic spatial model is different from the standard quantitative spatial model, basically in that you have frictional migration. Okay, there are different ways of how you can operationalize it, but what you need is that people will be imperfectly mobile across locations. Okay, our dynamic spatial model is special in the way, in the sense that we have forward-looking agents, and we are still able to invert quality of life from a transitory spatial equilibrium. This is a methodological contribution. I mean, that hasn't been done before for reasons that hopefully will become clear during the talk. It's a bit tricky to do it. But what we have is we have a model where we can acknowledge that mobility is frictional, and therefore it's very unlikely that we observe the spatial economy in a stationary spatial equilibrium. Okay, so we're going to be in a situation where we acknowledge that the data that we observe is most likely observed in a situation where some regions are growing, some regions are shrinking. It's still going to be an equilibrium in the model. We are going to endogenize the spatial arbitrage process, and still we can get to the fundamental quality of life in an approach treating that quality of life similar to a structural residual as in the Rosen-Rohrbeck framework. And yeah, I mean, so there are a couple of really important insights that emerge from this exercise. So the first one is that, I mean, that's actually fairly intuitive once you think it through. I hope I can make it clear over the course of the presentation. But one of the striking and really important insights that emerges from the analysis theoretically and empirically is that once you account for imperfect mobility, you start seeing much bigger spatial differences in quality of life than you would see in a frictionless model, okay? And this now has a number of important implications. I mean, the first one is that we have to completely rethink the way we think about the urban quality of life premium, because the urban quality of life premium turns out to be much bigger than you would assume if you just looked at the spatial economy, assuming a competitive equilibrium. And then all these local public goods that I mentioned before, right? Clean air, public schools, public transport, low crime rates. I mean, all of these things that economists in various literatures care about, all of these revealed preference-based evaluated goods turn out to have a significantly larger value, okay? So if you believe the model, if you believe what we do, you really, I mean, there is really a research agenda here to revisit the current workhorse estimates of various public goods, acknowledging that we probably have a frictional spatial equilibrium. Okay, but that's a very important policy conclusion. And then there is another thing that comes out from this model, which I think is really important for policymakers, because we have a situation in which there is imperfect spatial arbitrage, right? We suddenly end up with spatial incidence of quality of life policies or any other place-based policy. So let me say and stress what I mean by that. I think it's important because all over the world, you see policymakers trying to throw money onto selected regions in the hope that people in these regions are better off, okay? And then you have the Rosen-Rohrbeck framework where we say, okay, look, the utility by people in all regions is the same. It's fixed exogenously, right? There is a tension. I mean, why do you do this as a policymaker if you know actually that by assumption you cannot help people? So in this framework, because we do not have to impose any restriction on the utility, and we have imperfect spatial arbitrage, what's going to happen is that any positive shock to a region is going to trigger migration. People are going to go to this region, prices are going to go up, but this capitalization effect is going to be imperfect. And therefore, the people that you have targeted in those places, they will actually benefit. Or the other way around, if there is some negative shock, right? I mean, some region was badly treated by history, maybe because there was a trade shock, right? The compensation through lower rents will be imperfect, and therefore people will have a lower utility, and then you can start rationalizing why these people maybe vote for extreme parties, right? Something that you couldn't do with the Rosen-Rohrbeck framework. So two important insights. First, we can learn something about the distribution of amenities and the value of local public goods in a novel fashion. And the second is we can do counterfactual analysis with spatial incidence. Maybe that's the right point to quickly ask you if you have any questions about the broad aims and scopes of the paper before I start going into the details. So is the mission at least clear? I mean, very few of you have the camera switched on, so I can't see. You have a big screen in front of me, so if you had the cameras on, actually I could see you, but unfortunately I cannot see many of you. But I will just assume that I've been sufficiently clear in what I said, so that I can move ahead. Okay, so the mission is clear. What we want to achieve is I think, reasonably important. I mentioned this methodological contribution that gets us there. So to clarify that contribution, we've tried to summarize the papers that we are aware of that deal with migration frictions in quantitative models. Extremely nice papers, extremely well published, but coming out at an incredibly fast pace. So chances are that I'm missing something here. If you see one of your papers, which should be on that list, and it's not on the list, it's not intentional, we probably just missed it. So don't take it personal, let us know, and we are more than happy to add it to the list. What you can take away from this table essentially is that you have two classes of dynamic models. You have some models which are fully invertible, where you can get to structural fundamentals like quality of life or migration costs or many other things. But these models, which follow in the tradition of Desmet et al., right? I mean, the great JPE paper, these papers tend to assume static preferences. What we can do, we can bring to the literature a model where you have perfect foresight, and at the same time, you can invert all the primitives of the model. So we can actually get to the fundamental, which is called quality of life. Okay, maybe if you wonder, I mean, what's going on about this Mondras paper? I mean, Juan, doesn't he also have a dynamic model where he can get to quality of life? Yes, he can, but he has to take a shortcut, which is to assume that the economy is in a stationary spatial equilibrium, which is a bit inconsistent with the idea of a dynamic model, because once you're on a dynamic model, actually, I think you cannot really be in a stationary spatial equilibrium because you're constantly being brought outside this equilibrium by shocks. Yeah, our methodological contribution essentially is to fix that to some extent, I would say. So I think we have a point here. Cool. So this is the contribution in terms of the methods, in addition to the contextual contributions that I had before. I think we have actually quite a bit of time, so I can probably do some things that are fun, but which I don't normally do if we have less time. Let me show you some cool stylized facts, which are maybe not totally surprising, but they are just nice to see. And they're going to motivate in a very intuitive fashion what is going to go on in the model. So what you see here is super simple. That's just to show you that we know that in denser places, we have higher wages and we have higher rents, right? So there are costs and benefits of agglomeration, and both of that will be in the model. What I think is more interesting and also more closely related to the novel features of the model are these two graphs, because they show you how, or they give you a stylized impression of the way how we treat spatial arbitrage. So what you see on the left graph is a very simple scatter plot where we put on the x-axis the 2007 wages. So if you, to the right, all this is telling you is that you're an economically attractive region, okay? And then on the y-axis, we put the net migration over the subsequent decade. And what this is telling you is that people respond in their migration decisions to economic incentives.
Gabriel, excuse me. Clément Bosquet wants to ask a question. So Clément, I give you the floor.
Yes, hi.
Show your face. I mean, it's such a long time that we haven't seen each other. Switch the camera on.
I don't have a camera in my new office. I will have from next week, but I don't have it yet. I'm
Okay,
really sorry about that. So I just have a curiosity question about the slopes of the previous slides. The slopes of agglomeration economies and agglomeration costs. I mean,
yeah, you have to. I mean, this is they are not on the same scale. This is a 2. This is an 0.2, right? So this slope here to the right is a lot steeper than this slope. Therefore, of course, our congestion force exceeds the agglomeration force
by a lot. Okay.
Yeah, and it does so by a lot, and it has to do so by a lot because otherwise there is no stable equilibrium.
Sure.
Very good question.
Okay, thanks.
You haven't forgotten anything you learned at LSE, which is very good. All right. And this point that Clément just mentioned is really important, because here we now see that if you have a region which is very attractive in terms of wages, I mean, in the model, it's not going to be just about wages, but it's going to be about wages, prices, quality of life. But if you put that on a scatter plot, it gets very confusing. So I just show here, high wages lead to a lot of immigration. Fair enough, right? So that's one side of the migration story. So what is causing migration? And then the important thing in the model is that migration not only has to have a cause, it also has to have an effect. And the effect you see here, right? And again, this is, we haven't manipulated that. I mean, we really didn't do anything with this. This is purely descriptive. But what you can see absolutely clearly is that in those places where you see a lot of change in employment, so where you have a lot of people moving into the area, house prices go up. And they go up by a lot, right? And that is important for the model, because what's going to happen in the model, as you put more people into the region, right? Prices go up. This makes the attractive region less attractive, and therefore at some point you stop seeing migration. So this congestion force, I mean, this materialization of the congestion force in the right panel is what restores the equilibrium in our model. Okay, well, that's really important. And yeah, now let's look at some maps, right? I mean, this is just the same story in terms of maps. It's maybe also a nice way to introduce our setting. I mean, you can easily see that this is Germany. There is absolutely no particular reason why we use Germany. I mean, anything we do here, we could do with any other country. The only reason why we use Germany really is that we have really good data. So
Gabriel, excuse me. Eftimia wants to ask a question. So Eftimia.
Yes, please.
Yeah, hello. I'm wondering, is this at the country level? So we talk about migration that comes from outside Germany, or is this?
Yeah, that's it's very good to have this map here, because what this is supposed to show you is that this is going to be migration between these little local labor markets that you see here. So it's about domestic migration. I should be clear about that. So the model, by the way, can easily be applicable to any spatial scale. So I have arbitrary migration costs between all spatial units. There's absolutely no problem in adding additional countries, regions outside Germany. You would then empirically just identify higher migration costs between regions that are in different countries. That's absolutely no problem. It's an empirical problem because the model is, I mean, it has a huge data appetite. You need a lot of good data to quantify it, which makes it in practice rather difficult to apply to multi-country settings. But in principle, you could do that. What we are going to do here empirically is we're going to use Germany as a case in point, precisely because we have really good data that allows us to observe migration between spatial units. And the spatial units are these local labor markets. I mean, you can think of them as commuting zones. Okay, so it's something like a self-contained functional urban area. And and we have 141 of them. And for these units, we create all kinds of indices. We do not only create our indices for these spatial units, we also distinguish between 18 different groups defined by skill, gender, and age. So there's also a lot of heterogeneity going on here. The data, by the way, I mean, it's fantastic data. It's close to 30 million German workers, which we track over space and time, so we can go back in time and see where has a worker lived and worked, and what was the wage they earned, and where are they in the next period. It's the universe of social security workers, so it's basically as nice as it gets, and therefore you can measure wages and also migration very precisely, and you can do the perfect mix adjustment when you compute the wage indices. It's just, I mean, very nice data, which is why we do it for Germany. And then again, you see the story that you saw on the scatter plots before. You see some regions which have very high wages. You see that actually they experience positive net migration. The correlation isn't actually perfect, right? But where the correlation is really strong, and this is what matters for the model, is that in places where you see a lot of in-migration, for instance, in Berlin, you see really rents going up a lot, right? And that's really important for the model. And that's actually the intuition behind most of what is going to go on in the model, really. Yeah, so I hope that makes sense, and I hope that gives you a little bit of a flavor in terms of what's going to go on. And let me now cover a couple of things more formally. That's the boring stuff. I don't going to go too much into detail, but let me say that in principle, we think about the worker who lives today in the location I. The worker has lived in the previous period in K and lives in the next period in J, right? So there's always a little bit of a migration sequence that matters here, but in principle, workers only exist, I mean, similar to quantitative spatial models, as hypothetical constructs, right? With some tastes that are going to be drawn from some distribution. The actual unit of analysis in the model is not the worker, but it's a combination of group, region, and year. So that's the unit for which we are going to quantify the model. The consumption side is as simple as it gets, and it's pretty much the standard that we've seen in the literature for a long time. So we're going to have a Cobb-Douglas utility function. People consume a basket of tradable goods and one non-tradable good, which is housing. And quality of life enters the utility function as a utility shifter. Standard. Production is even simpler. The tradable good just has one factor of production because we only really need that, right? Labor. I would have added capital, but Fabian, for some reason, doesn't like capital in the production function, so we have dropped it because we don't need it. Fair enough. Perfect competition. That means wages directly map into productivity. We have exogenous and endogenous productivity. Exogenous productivity will just come from stuff like a nice connection to rivers, slopes, and so on and so forth. I mean, it's a structural fundamental. And the endogenous component is the standard agglomeration economy that is a function of density, which I just showed you before. Housing, Cobb-Douglas, now we have capital and land, two production factors. One of them is inelastically supplied, that's land. This generates the congestion force. So under market clearing, whenever you have more people, you have more demand in a labor market, you're going to end up with higher house prices. And then there is some total factor productivity shifter, right, which you can use to rationalize differences in regulation and geography. Yeah, I guess that's pretty straightforward, right? This here is maybe a little bit more interesting in the context of how we parameterize the model. The left graph really just shows you some migration probabilities, and I mean, it's for one thing we want to show you that we have many different groups in our model, which is cool. But more importantly, we want to point to your attention here. I don't know how well you can see it, but what we've done is we have computed in our data the number of times people change the local labor market in which they work over their entire employment lifetime, which means 40 years during which they have been in employment. And I mean, for those of you who work on domestic migration, that's not going to be a surprise. I was actually a little bit surprised that people really move very little. So the mean number of changes between local labor markets in our data is pretty much 1, right? So over their employment biography, right, the mean worker changes the local labor market exactly once. And even if you disaggregate this by groups, you find very few groups where this number is significantly larger than 1. So one big takeaway from the data really is that migration costs at the extensive margin, they must be really high, right? In order to explain why you have so little migration across regions within the country, which is institutionally pretty well integrated. I mean, there's just got to be some sort of migration costs that keep people rooted.
Gabriel?
But it's not, yep, go ahead.
But this mean of 1, it's a lot of people that don't move a lot and a few that moves a lot, no?
Yes. So I think I think the share of people who do not move at all is probably 50% or something. Yeah, you're right.
Okay.
Yeah, that's true, right? That's something to keep in mind. The other thing that is important, and that you know from migration research, I mean, there's a lot of reduced from migration research that has established this before, but I think it's just kind of good to look at this again and to remind oneself, conditional on making a move, right? Even within a small country like Germany, people do not really move in a spatial random pattern. I mean, you could imagine, I mean, Germany is so small compared to the US, whether you live in the north or in the south doesn't really matter. No, I mean, it seems to matter apparently, because if people move, you have a much higher chance of moving over short distances than over longer distances. Okay, so you probably also want to have a model in which you have some sort of intensive margin migration costs. And I guess this is why I'm showing this to you, right? I want to motivate the model, so the model is going to have an extensive and an intensive margin migration cost, right? And the intensive margin migration cost can differ arbitrarily in anything, but distance is going to be one of the factors that could explain variation in migration costs. Cool. So now we get to the more interesting or the more original parts of the model. Now we need to formally model the migration decision. So imagine that I'm living in Berlin, I'm here in Berlin now, and I'm thinking about where to live in the next period. So what am I going to do? The formula looks a little bit involved, but the intuition is super straightforward, right? What I'm going to do is I'm going to think about the location, which is going to maximize my expected lifetime utility. Okay. What goes into my lifetime utility? We have a net present value formula. We have a couple of positive revenues. So it's just one-to-one like in financial economics. My streams of revenues are going to be my expected utilities. And I have to discount these streams of revenues by the migration cost that I would experience when I were to move to a location. And then I just compute the net present value. The reason why this formula looks a little bit involved is because it considers a sequence of moves in different years, right? So we have here, this is a very general case where you can move in the next period to J, in the next period to M, and so on and so forth. And therefore you get a lot of terms, right? But what is actually going on here in the formula is that eventually your migration, your returns to migration are going to depend on the things that enter this letter, which we call V. And what is V? V is simply the indirect utility that you expect in a certain period. And this indirect utility then simply depends on wages, rents, quality of life, and an idiosyncratic component, which you can think of something unforeseeable happening at the individual level that is specific to a worker. So for instance, if I have a new romance in another city, this is going to give me a big boost to utility if I move to that city, right? So it's that really what's going on. So eventually, you have this straightforward indirect utility function. Of course, if you make a decision to move, then you have a tau. Tau is the migration cost. You're going to lose some social capital behind. You have to rebuild that social capital at the destination. That creates a cost, right? And in this trade-off between potentially higher wages, lower rents, high quality of life, you name it, right? And on the downside, the migration cost of getting to a certain destination J. In this trade-off, you make your migration decision. Yeah, so how do you solve that? I mean, we do nothing particularly exciting. We assume that this idiosyncratic component is drawn from an extreme value type 1 Gumbel distribution. And then you can just work out the standard maximization problem in the spirit of McFadden. This gives you this actually pretty nice conditional migration probability. So I think that this is probably more intuitive than the equation that you saw before. Let me spend a second to just point out what you see here. Psi iji gives you the probability at which a worker is going to move from the location J to from the location I to a location J. Okay, it's going to depend on V. Right? V contains wages, rents, and quality of life. So if I have a higher wage, this is going to increase my Xi. If there's a location J with a high wage, I'm more likely to move there. Okay, the opposite is true for rents. Then you have the migration cost, very intuitive. So if going to J is very expensive, I'm going to be less likely to move there. We have a B here, which is a structural residual, which essentially rationalizes the data, because in different years, even for the same group, you see different migration flows. So you find a way to rationalize that. And this is going to be essentially a group-specific shock. So that's maybe not so interesting. What is really important now is the gamma. So the gamma is going to be a taste dispersion parameter. And the intuition is that if gamma is very large, you have a lot of homogeneity in workers. So with gamma equal to infinity, right? I mean, everybody is exactly the same. And what that means is that relatively small changes in wages are going to lead to massive adjustments in migration probabilities. Okay, so even tiny little differences in wages and prices are going to lead to huge migration flows. However, if I set gamma to 0, right, then the opposite happens. Then we have, I mean, that's actually not theoretically possible, but let's make gamma very small. So if gamma is extremely small, then only very few people will migrate, even if you have very large wage differences. So this is why we call this a migration elasticity, because it moderates in a way the speed of adjustment in the spatial arbitrage process. Yeah. It's a very critical parameter that we have to estimate. Yeah, so that's really it, right? I mean, so you have the migration pull factors, which are all in the V. You have the migration cost, and then you have gamma, which moderates how quickly migrants really respond to economic incentives. These conditional migration probabilities allow me to compute all the migration outflows from any migration origin. If I have all the outflows, I can compute all the inflows to the destinations. If I have all the inflows to the destinations, then I get the next period number of people in that region by group, right? And the beauty of the model is that it is engineered in a way that you can map directly from employment to wages and rents. So once I know all the employment in the next period, I also know automatically what the wages and what the rents are going to be in that period. This makes your life in a dynamic model a lot easier, which is why we did it, I guess. Is that clear? I mean, maybe this is, I mean, this migration equation seems rather fundamental, so it would be good if everybody's on board with the intuition. No comments in the chat? Okay, good. So I take that as a positive sign. Yeah, what else do I want to tell you, which is absolutely necessary? I mean, let me just, yeah, maybe just speaking about the spatial equilibrium condition. It's a fundamental step from the quantitative model to the dynamic model. We now have a transitory spatial equilibrium in which we rationalize the data, right, in a non-stationary situation. What do I mean by that? I mean, I still have a lot of equilibrium conditions. I mean, even in the transitory spatial equilibrium, we need a lot of market clearings. We need market clearing on all good and all factor markets, okay? So there's not going to be unemployment or something like this, right? So the economy is frictionless in a spatial sense, but of course, we assume that we have frictionless labor markets, right? And the same goes for good markets, housing markets, and so on and so forth, right? But, and that's important, we can have unbalanced migration. So we can have something that we call an equilibrium, but still you have some regions that grow and some regions that shrink, right? Just like in the real world, you're going to observe if you look at the data in France right now, that some regions are growing, some regions are shrinking. And this is still an equilibrium here in our model. That's what we observe. And then there is something which we do not observe and to which we can only get through the model, and that is the stationary spatial equilibrium. So we're going to have some situations, right? I mean, some regions are growing, some regions are shrinking, but eventually the migration, right, in the long run, if there were no further shocks, right? Imagine there was a trade shock, right? Some regions were hit negatively, right? I mean, now people are leaving these regions, right? Therefore, these regions are shrinking. That means that prices are falling, the regions get more attractive. If there was no further shock, at some point, migration would do the trick to lead to a stationary spatial equilibrium, after which the employment vector would be stationary. That's a situation which is never going to happen in the real world, because in the meantime, you're going to see different spatial shocks. But it is a notion of a spatial equilibrium which exists in the model, and which I think is quite useful for policy analysis if you want to think about the counterfactuals in the comparative static sense. And yeah, and then you have the dynamic equilibrium, which is just a collection of transitory spatial equilibria up to the point where the economy reaches the stationary spatial equilibrium. Okay. Yeah, so I think I should briefly mention something how we model worker expectations. I've been stressing that we have perfect foresight, but there is one caveat, and I don't want to be silent about that. So when I say we model perfect foresight, what I mean is that we we allow workers to perfectly anticipate all future wages and prices as they endogenously materialize within the model. So everything the model knows, workers will also know that. Of course, what workers cannot know is if there are some exogenous shocks, right? I mean, there's no way you can know that actually in the next period, some exogenous technological change will favor some regions more than others. I mean, workers just don't know that, and they also don't know that in our model. And they have some bounded rationality, if you want to say, so in the sense that we are going to assume that people, when they make migration decisions, they go to a place in the expectation that they're going to stay at that place forever. Okay, and this is motivated by the fact that we see so few moves that we think that is a reasonable assumption. What we do in an extension in the appendix is we allow people to move to a place in the expectation to relocate once more to another place. Okay, that already adds to the complexity of the model. We do it, we show that the changes in any respect are rather marginal. If we were to go to one more move, then I mean, it becomes just computationally intractable. I mean, the model is quite demanding in terms of the computational exercise that has to go into it, and more than 2 moves. I mean, it's just not possible. But we think, given that people move so irregularly, the assumption that you go to a place, you think very carefully about what's going to happen at that place. So you think, I mean, our wage is going to go up, our price is going to go up. I think that's really important, right? I mean, the idea that you just go to a place because then from that place you can migrate to yet another place, that's probably not the first order concern we should have here. That's at least my view. Good. And yeah, so with this, we can come to the intuitive version of the model, which is unfortunately actually not so intuitive. But I think I mean, are we doing well in time? I mean, I don't know. I guess so, right? I mean, so we have 1.5 hours. So
time.
Plenty of time, yeah. So let me try to give you the intuitive version of the model. So what we've done here is we have tried to collect all the housing market related equilibrium conditions in these upward sloping lines. So what this tells you is that if employment in the region goes up, right, real living costs go up. And the reason why real living costs go up is because house prices increase, because land is inelastically supplied. This curve goes up less than you would see if you were just looking at house prices, because not only prices go up, but also wages go up, because you have an agglomeration return. Okay, but still, because the agglomeration cost exceeds the benefit, right? I mean, this is back to Clément's point. This is a positively sloped curve. Okay. What I've done here is I've taken 2 cities, one city with a solid line, one city with the dashed line. The dashed line can offer lower living costs at any city size because it's more productive on the housing market. Maybe it's less tightly regulated. Now, there is also a kind of a demand side. I mean, if you, in a way, you can think about this as supply side related. This is a demand for living related curve. So what this curve here shows you is the demand by people for living in a city. Okay, it collects all equilibrium conditions that we have that relate to migration. The intuition is actually not very complicated because we have taste heterogeneity. Okay, so I live in Berlin and I like being in Berlin a lot, right? But Fabian maybe, or Duncan, they don't live in Berlin and probably they don't like being in Berlin so much, right? So whereas I would be happily living in Berlin at the current real living cost, or possibly even at higher real living cost, in order for Duncan or Fabian to be in Berlin, we probably would have to decrease the real living cost by a lot, simply because they have lower tastes. That means that we get this negatively sloped curve, okay? Essentially, the cheaper it gets, the more people want to be in Berlin. At the same time, of course, there is something that can shift demand, and here it's quality of life. So all else constant, if I somehow manage to improve the quality of life of Berlin, people would have a higher willingness to pay, okay? So in a way, what we see here are two different cities, solid and dashed, right? And they differ essentially in quality of life. Now, how can I get to quality of life in the model? Basically, what happens is that I observe everything I have to observe related to housing markets, okay? I can estimate all the relevant parameters. I can back out the fundamental productivity. So I can observe the city size of a large city like Berlin. I can map it to the housing market curve of Berlin. And then I can fit this demand curve such that it intersects with this intersection point. And then I can do the same thing for a smaller city, right? Take the small employment. I map it to the housing market curve of the smaller city. I fit the migration demand curve again. And then this difference that I see here is going to be my quality of life residual. The reason why I'm pointing this out here is because you can see why necessarily the Rosen-Rohrbeck framework gives you a lower quality of life premium in the bigger city. And the reason this is true is because this slope here, this negative slope, is determined by the migration elasticity gamma. So we have estimated this migration elasticity gamma. It's relatively small. If I now start increasing gamma, I make people more and more mobile. In the limit where people are perfectly mobile, this curve becomes a horizontal line, right? So these yellow lines here that you see, they are essentially our model in the special case of Rosen-Rohrbeck. And if I do the same exercise here in Rosen-Rohrbeck, I mean, you can easily do this in your mind. As you kind of flatten the slope of these two lines, you see how this quality of life residual here necessarily shrinks, right? And then this particular point here, we've kind of shown here a special case. In this special case, it can even go so far that under Rosen-Rohrbeck, you would conclude that the bigger city has a lower quality of life, whereas in reality, it actually has a higher quality of life. And what's the mistake that Rosen-Rohrbeck is doing? Rosen-Rohrbeck is not taking into account that Berlin actually needs to be a very attractive city if it managed to attract so many people, some of which have actually even distastes for being in Berlin, right? That's the intuition here, right? So I think it makes actually quite a bit of sense intuitively. The graph is a little bit cumbersome to go through, but I think the takeaway is actually straightforward and is important. Yeah, so that's the theory. I mean, I'm going to stop with the theory now. The rest is going to be much more empirical. So if you want to ask something about the model, maybe now is a good time.
Some questions?
Nothing in the chat?
No.
No?
No.
Okay.
Nothing in the...
Oh, awesome, right? So with this theoretical model out of our way, let's talk about the quantitative part. So I mentioned it before, we have 141 local labor markets. They are all connected to each other through migration. We have 18 groups defined by age, gender, and skill. So one group could, for instance, be young female workers with tertiary education, just as an example, right? And for all these 18 groups and all these 141 labor market regions, we can, of course, easily compute migration because we have the full employment record, essentially, right? We know all the 28, close to 30 million workers, where they were at different points in time, which allows us not only to compute the total employment, but of course, all bilateral migration flows between these regions over our study period, which starts here in 1993. In the graph before that you saw with the number of moves over the careers, I mean, it's West Germany only, but a much longer period. So based on this employment data, we construct migration flows, and then we do house price indices. This is based on about 20 million observations from this ImmoScout database that people tend to use. It's the best you can get. Maybe the only thing I should mention here with the house price index, which is a little bit different than what most people do, I follow Laurent, Pierre-Philippe, and Gilles in their approach to compute the house price index at the city center, right? So these house price indices, they're not only mix adjusted for structural characteristics, but also for location. And I think this is important because if you think about quality of life, then you want to measure this at the center of the city, because as you move away from the city center, house prices go down, but this decrease in house prices only compensates for commuting costs, right? So if you really want to get the quality of life, net of commuting costs, you got to measure house prices at the city center. So I do what Pierre-Philippe, Laurent, and Gilles do, and do this kind of locational mix adjustment. Other than that, it's a pretty straightforward house price index, nothing really special about that. Yeah, then we get a bunch of parameters to estimate. So let me just quickly remind you guys for how you work with these quantitative models. So you have a model that puts a lot of structure on the data in a way, right? If you want to quantify the model, what you first have to do is you have to derive estimation equations from the structure of the model to estimate structural parameters. This is what you see here. Okay, structural parameters can be things like what's the housing supply elasticity, what's the agglomeration elasticity, okay, what are the bilateral migration costs. All of these things are parameters. And then once you have these parameters, then you can use the data and the parameters and the structure of the model to get to the unobserved fundamentals, which would be something like quality of life or fundamental housing productivity, fundamental labor productivity, these kind of things. So we have to actually estimate a lot in this paper. I mean, it's maybe it sounds more like a theoretical paper than an empirical paper, but there's actually a lot of econometrics going on here. What we do is we basically pick the papers from the literature that we like most in these different literatures and on housing, labor, migration, and we just replicate what is seemingly the state of the art in the literature. The advantage that we have is that we have this super cool data set. So rather than having one agglomeration elasticity, we get 18, right? Rather than one migration elasticity, we have 18, right? And which is something that nobody has done before, right? So in a way, if you're interested in the empirics and in these particular parameters, I think looking into our appendix can be quite interesting. Other than that, my sentiment is that this is not the primary contribution of our paper. So I'm actually inclined to skip the estimation of these parameters unless you are interested in the specific estimation strategy. Then I would click on one of these buttons here and talk about how we did it, if that's all right for you guys. So just think about it. I mean, if you're interested in some estimation of these parameters, right? I mean, then ask me. In principle, we find parameter estimates which are within the range of the literature, right? And also the heterogeneity is within what you would expect. I mean, for instance, the agglomeration elasticity is between a little bit more than 0 and 4%. And of course, it's larger for the high skilled. So you have skill bias returns to agglomeration. It's nothing thought-provoking, I would say. What is a lot more interesting, and where I think we take a bit more pride in having solved a rather tricky problem, is when we come to the inversion of the model. Okay? Now we have all these parameters. Inversion is where you get to the structural fundamentals. Quality of life here clearly is the fundamental we are most interested in, but it's also by far the fundamental which is most difficult to come by. So really the model is built, that you have this really nice mapping from employment to wages and rents. How does it go? Essentially you have the first order condition of labor demand, right? And that really takes you from the wages that you observe to the productivity, and then you can split productivity into what you can explain with density, and then the residual, that's the fundamental productivity. Super straightforward. And the same on the housing market, right? We have housing market clearing. Therefore, we can go from demand for housing, which essentially is a GDP. We can take that. We can take the rents that we observe, and we can uncover the unobserved fundamental housing productivity, assuming land market clearing. Okay, that's very simple. Now, when it comes to quality of life, it gets a little bit more difficult. And the trouble is that we have forward-looking expectations. So people, they anticipate already when they migrate what is going to happen at that destination in terms of wages and rents. I'd be actually quite interested in your view on whether this is a plausible assumption or not. We also do it actually, we also do everything with static preferences, static expectations in the appendix, just to figure out what it does. We started with static expectations, which is what Esteban, Rossi Hansberg, Klaus Desmet, and David Nagy do in their paper. But then we were told by dynamic people that you just cannot do that, right? That you cannot solve the problem, right? But by making people stupid. So you really have to have them forward-looking. I think we can debate whether people in reality are that smart that they can really understand what the future evolution of wages and prices will be. I'm certainly interested in your thoughts on that. But eventually we had to deal with this because people wanted us to deal with this. And the problem this causes is the following. Okay? Let's just assume for a second that I know all the future wages and rents. If I know all future wages and rents, what I then can do with the standard fixed point algorithm, I can back out quality of life. That's really just the same. Not exactly the same, but it's very similar as you would do in a quantitative spatial model. It's a numerical solution approach we do all the time in quantitative economics. That's easy. The problem is that the only way for me to get to these future wages and prices is to use the model to forecast it, right? So I use the model, I predict future migration, changes in migration map to changes in employment, changes in employment map to changes in wages and prices. So there's a circularity problem here, really, right? You need these vectors here to get to A, but to get to the vector, you need A. That's a problem that the literature hasn't solved so far. So you have the people like Caliendo and co-authors, dynamic guys, who take the model into kind of first differences using the Bellman principle, which is fantastic and essentially gets around this expectation problem. But the cost is that you cannot actually easily solve for A. Or you have the people like Esteban and his co-authors who say, okay, let's have a model which is invertible, but then you don't have foresight. So what we do is we just create a slightly involved nested structure of programming algorithms, which allows us to identify A and then these future wages and prices as one fixed point problem. Yeah. So I don't know how interesting this really is, but the intuition is, I mean, we spend a lot of time fixing this problem, so we are quite proud of it. So I like talking about it, right? Even though probably to anyone in this room, this is much less exciting. But the intuition is we have different programming algorithms. So we have this red guy here. What the red guy does, it takes guesses of wages and prices in the future. And for these guesses, the red guy computes the quality of life. Then we have this green loop, and then this green loop essentially takes these values of quality of life and computes future wages and prices. And then you have a blue loop, which kind of inputs the output of one algorithm as an input to the other, and vice versa. And then this whole procedure goes on and on and on and on until you have an internally consistent solution. And it works fairly well. I mean, you can do some shortcuts to speed up the computational time, but eventually you have a model that nicely converges as long as agglomeration costs exceed agglomeration benefits, and you can do the Monte Carlos, and you can actually show that it's all pretty stable. So yeah, so that is in a sense the methodological contribution that I mentioned before. A non-trivial thing to do, but it works. And then what this programming algorithm really gives you are these beautiful predictions of all outcomes into the future. So this is one slide for Berlin, but we have it for every labor market in Germany. What this is showing you here is that the model believes that over the next 1,000 years, right? Although almost everything is going to happen within the next 100 years, right? And most of the adjustments happen actually within 30 years. So what the model predicts is that the employment in Berlin is going to increase from about 1.45 million to about 1.6 million workers working. So this is, of course, just a fraction of the population. You have pensioners and you have students, and they all don't count. So population increases, wages are going to increase, partially because of agglomeration returns, but also partially because there's a lot of sorting. So what you're going to see in Berlin is that the share of high skilled is going to go up. And then because you have more people in Berlin and people have more money, of course, you have more housing demand. That means that you're going to have higher rents. And then because you have higher rents, housing consumption decreases, right? So for the high skilled, you're going to see something like per square meter, housing consumption is going to decrease, not by a lot, by about 36 to about 35 square meters, right? So that makes me feel happy that I actually bought my property, so I'm not going to be affected by that. But if you were to rent in Berlin, you would have to anticipate that actually in the long run, your housing consumption is decreasing. So yeah, I mean, I think that's cool. I mean, one thing we did, and which I should maybe mention here because I have the time, is now you can wonder, I mean, how good is the model actually in doing these predictions? And I should say that I don't necessarily expect the model to be good, because this is not forecasting in the sense that I try to explain the real world. What I'm trying to do here, I'm forecasting a hypothetical scenario in which no unexpected shocks happen, right? But still, right, even though we do not expect the model to be necessarily doing extremely well, it actually is pretty good in its out-of-sample predictive power. So if you take here the year 2007, and you only use data from 2007, nothing else, just 2007, and then you ask the model, please predict the next 10 years in terms of employment by region, or even employment by region and group, and then you compare that to the changes in employment that actually happen in the data, you see a very strong correlation. For region employment, the relationship here, the slope is even close to 1, which means that on average, we make a pretty small prediction error, right? And that's, I mean, that's not really telling us that the model is a good tool for predicting the future, but it does tell you something. I mean, it tells you that the model probably is relatively good in predicting mean reversion in the data. So the way the economy converges back into the stationary spatial equilibrium. And that probably also tells you that mean reversion is an important feature of the real world.
Can I ask you a question, Gabriel?
Absolutely. Yeah, go ahead.
Well, I like your pictures, but when I looked at them carefully, for example, for the gross wage, the change is very tiny. So you go from 3.7 to 3.73 for so many years. So you have an increase, but that's not a very big increase. So that does not change much of what is happening in terms of levels. And then my second comment is that you don't put any shock. So everything depends on your initial condition and how you have estimated the initial condition and the parameters that will give you the long run. So if you change a little bit the parameter, are you going to change those curves a lot? Well, it's a question I would like to ask to you. So that
I mean, so the effects here on the wages, they are relatively small. That said, I mean, this is what I would expect, right? Because I see, I mean, it's a mild adjustment in employment that I see here predicted for Berlin, right? What are we talking about? 200,000 additional people. And the effect on wages here comes primarily through the agglomeration effect. Now, Berlin is already a big city. Adding 200,000 people, I mean, at the agglomeration elasticities that we have, only allows you to expect a limited effect on the wage, right? Maybe a bigger effect could happen through the change in the share of high skilled. Now, that change is also relatively moderate. Maybe Berlin is not the best example. I mean, we just took it because it's the biggest city in Germany and seems uncontroversial. Maybe we can find some cities where you have bigger changes in employment, and then you would also see bigger changes in wages and maybe also greater sorting effects.
So you claim that the changes are big. That I'm surprised you to say that. I think changes are small.
No. I mean, I think the changes are pretty much what I would expect. That's what I was saying, right? I mean, so I think 200,000.
Why would you expect a small change?
Because the agglomeration elasticity is small. I think the canonical view of the agglomeration elasticity net of sorting is 2%, right?
Yes, but it's my opinion. Maybe you can correct me, but my opinion is that the change that you get here is depending on the initial condition and the long run, which will depend on the parameters, and they would be highly dependent on the value of some parameters.
Absolutely.
So you could present a figure where the gross wage goes down by changing gamma or delta, which one?
So that's a good question. This is a good. I take your point that of course these predictions are going to depend on the parameter values, right? That's clear, right? And so maybe what we could do is we could take some lower bound and upper bound values of these parameters and try to figure out actually how sensitive this is. It's a good point. People don't do this probably because these models are already computationally so demanding that if you now start to play around with parameter values, then it just becomes a little bit cumbersome. What you could do is you could take upper bounds, lower bounds, and see how sensitive that really is. Frankly, what I kind of sense is that a lot of this adjustment in the long run comes eventually from the migration flows that you observe, right? So these parameters are estimated eventually from migration flows that you observe, right? So you are in a converging economy that rationalizes the data in a certain way. So the model is going to assume that, if this is a growing region, then it has relatively high fundamentals, higher fundamentals than you would rationalize if you just took the current levels without checking the flows, and this is going to drive a lot where you converge to in the long run. But it's, I think your point is right. I mean, in all of these models, I mean, this is not just concerning this model. You actually, in the perfect world, you would want to do more in terms of sensitivity with respect to parameter values. Yeah. Yeah. So this is that's what goes on in these convergence. I mean, at the end of the day, I mean, this is as much as I like these plots, right? I mean, they're kind of nice and funny, and it's interesting to see that we actually predict the mean reversion reasonably well, right? I mean, you say these changes are small, but then as I showed you, right? I mean, for the 10-year period after 27, right? I mean, it's pretty much the change on average that we see in the data. So what the model, it under predicts what happens in the real world by 15 to 20% on average, right? But we are relatively close to the real changes, which means that, I mean, that's probably what mean reversion does, right? And the rest that happens due to exogenous shocks. I mean, where I would never claim I can make any prediction. I mean, how do I know what the next trade shock is going to be and which regions are going to be hit positively or negatively? If I knew that, right, I'd be a millionaire because I started speculating with the stock market, right? I mean, just can't do that. Cool. But as beautiful as this is, the actual point of the paper is to not to really look at these adjustments and endogenous variables, but really back out the exogenous variable, which is the quality of life.
Yeah, you may want to speed up a bit on this part so that we can wrap up. I mean, we can finish within 10 minutes so that we can have questions afterwards.
Okay, 10 minutes. All right. So let me. That's a good point. So we have 10 minutes. So I do this quickly. So big takeaway. So now take the quality of life that we have inverted from this model, put it on a map, and compare it to what you would get if you did Rosen-Rollback, essentially with an infinite migration elasticity. You see that in Germany, even under Rosen-Rollback, big cities tend to be places with high quality of life, i.e. rents are relatively higher than wages. But the difference, the dispersion, right, in these amenities is a lot bigger if you look into our model. The scaling here in these two maps is exactly identical. The fact that you see more dark and light shaded regions means that you have more dispersion in quality of life. You can do this for all 18 groups that we have, right? We have 18 different groups. If we had the same dispersion in both measures, we would be along the 45-degree line, but you can see that we are pretty far off the 45-degree line with all the 18 different groups, right? So for each group, we underestimate the spatial quality of life difference in Rosen-Rollback. And that gives you the effect more or less directly, actually, on the valuation of some non-marketed goods. I mean, this is a relatively long table in the paper. I've just cut it short. I just want to point out some parameters here. I mean, you see that if you look into the urban quality of life premium, we are about 3 times larger if we correlate our structural residual with city size in the dynamic model as opposed to Rosen-Rollback. For pollution, the negative effect is much greater, twice or a little bit more than twice as large, right? For some things like opera houses, we find a positive effect, which you can't even detect in Rosen-Rollback, and so on and so forth, right? I mean, I don't want to really bore you with this, but that's really the consequence, I mean, of all of this theoretical feature of the model. The consequence is that necessarily you attach greater values of non-marketed goods in the standard valuation procedure than if you were to use Rosen-Rollback. Okay, that's quite important. Now I have a couple of minutes, and this is just to confirm that really, I mean, as I increase gamma, really this difference fades away, right? As gamma goes to infinity, as people get really mobile, then we also convert to the Rosen-Rollback amenity. Yeah, let me just show you a couple of counterfactuals and then I stop, right? Because these counterfactuals, I think they are also very cool. I talked about them at the beginning. Now we want to use the model to say, okay, what happens if we change the quality of life in a certain region? Okay, and now you can take any arbitrary quality of life shock. I've made one up, right? I've simply assumed here that we are going to improve air quality in the most polluted areas of Germany. Okay, this is a policy similar to the Clean Air Act in the US, right? And if we did something like this Clean Air Act in Germany, what would we guess? Okay, and I can show you 3 maps that pretty much tell the story, right? This is the quality of life shock. And it shows you that in some regions here where you have a lot of exposure, in particular to coal power plants, the air quality would increase by quite a bit. The consequence would be that people would be moving to these places. So the rent price will go up, right? But unlike in Rosenrollback, the rent will only go up to a point that people will be imperfectly compensated, so that eventually you end up with a positive utility effect in these targeted regions, right? Keep in mind, in Rosenrollback, really what you would see here would just be a one uniform colored map, because by assumption, there cannot be a utility effect, right? So I think that's a pretty nice tool from a policy perspective, because you really, it puts you in a position as a policymaker to make predictions about welfare effects at a local level that take into account the frictional nature of mobility, right? So you can actually help people in struggling regions. And then there is another set of counterfactuals, and that I just going to quickly mention and just summarize here in a couple of sentences. We've done a hypothetical thought experiment because we thought it's interesting to see that quality of life is the quality of life, the urban quality of life premium is so big, right? So you kind of wonder, I mean, in this world in which we are now, where we are thinking about, okay, what would happen if cities change because of COVID, and many people are concerned about people no longer working at the offices, therefore agglomeration economies disappearing, right? And it turns out that if this was true, right, I mean, if agglomeration economies completely disappeared, you would see a drop in economic activities in big cities, and people would be moving to small cities. But if you trust what we did to approximate the big city effect on quality of life, it operates through social interactions. We use a little bit of social media to do some ambitious exercises here. If you trust these calculations, what would come out of the model is that a shock, a COVID shock to quality of life of a city could have far bigger effects actually than the agglomeration shock. And this is just another way to say that in our model, no matter how important agglomeration effects on productivity are in the literature, what is actually driving concentration, spatial concentration, even more so in Germany, is the urban quality of life premium, right? And I don't go further into details of this counterfactual, right? And just finish with mentioning that you can use our model to do counterfactuals in any structural fundamental, right? This is by no means limited to quality of life. You could also model a trade shock by changing fundamental productivity, right? You could change migration costs, internal or external migration costs. You could make it easier for people from other countries to migrate into Germany, right? You can play around with any parameter or any fundamental, and you can run these counterfactuals in the frictional equilibrium, which I think is a pretty cool thing to do, and has many applications. And yeah, so that's it really. Ben?
Gabriel, we thank you for this excellent presentation. Now we move on to the part dedicated to discussion or questions. So would anyone like to start asking a question?
I have a small question.
Yeah.
Yeah, thank you so much. It was a great presentation. I just want to ask a question on the last air quality exercise. So in this air quality exercise, you somehow assume that air quality improves, right? But you don't somehow account for any cost of this environmental.
Yes, absolutely. So what we do is actually we do we do a lot of work when it comes to identifying the value of air quality. We have these windrows instruments, right? So we identify the whole air pollution effect from the fact that in Berlin you have winds that blow from the southwest, and then we have kind of we adjust distances for winds, we control for the standard market excess and for anything that is spatially correlated, and identify the pollution effect from how much the wind actually skews the exposure to pollution from coal fields. That we do. But what we do not do is to now do something like a cost-benefit analysis. So we have actually welfare effects where I can show you how temporally these effects materialize, and I can also show you all the benefits, also how the benefits depreciate once you account for spatial inequality and you don't like inequality. But I end here at the value of 20 billion, right? That's the inequality adjusted benefit. And now to really decide whether the policy that gets us there is good or bad, you would have to do some cost exercise and see if the costs are less than 20 billion. That we haven't done because I think, this would be yet another paper in the paper. And I think at some point, we also have to admit that there are certainly people who could do this costing exercise much better than we could it, right? So I prefer to leave it to them, but I agree with you, of course, we just did half of the exercise.
Yeah, but you have calculated the benefits. So as you say, it is easy to compare it with any potential policy that will improve air quality and will cost that much. Yeah, thank you.
We have time for a few more questions, so please feel free to ask for the floor. No more questions? Yeah, I have a comment concerning your instrument of air quality based on wide dispersion of pollution, right?
Mm-hmm.
Have you tested another instrumental variable, because it could be very different estimates with another instrument?
Do you have one in mind?
For example, for example, I think to use thermal inversion in the atmosphere. There is recent papers of Antoine de Chevalpêtre, for example, which use at NOx3 level, so very similar level, spatial level of aggregation as your paper, which use this thermal inversion, because that's a very good predictor, meteorological predictor of pollution and persistence of pollution.
No, that's good to know. No, we didn't. I think none of us really came up with this idea. We are no environmental economists. We came across this wind instrument in a couple of papers that were recently published, but the thermal inversion approach, I wasn't aware. So we will certainly search for that and check if this gives us similar results. Yeah, thank you. That's very useful.
Yeah, well, welcome. Another questions? No? So one last time, thank you, Gabriel, for this presentation, and thank you to all the participants. The next seminar will take place next month, April 8th, and we will welcome Tidiane Lee from University of Lugano, and he will present to you her work on fiscal competition, tax competition. One last thing, for non-French speaking people, we would like to attend seminars when the presentation is in English. I invite